Now let's first look at blackbody radiation. This graph here display the spectral radiant excitant, or rather the spectra of emission from a blackbody radiator. Now, when the blackbody radiator is at a temperature of 300 K, you probably would see a continuous spectral distribution that looks like this. And then at 400 K, the spectral radiant excitant would be higher, and you can see that the peak is shifting to shorter wavelength. And then at 600 K, which we consider as white hot, that's really hot now, and you see that the peak of this spectrum is actually occurring probably around blue region. This is around yellow, and this is in the infrared. So what do we mean by a black body? Well, a black body is actually an ideal absorber as well as a perfect emitter of radiation. And associated with the excitance or emittance from emission from this black body, which is at a particular temperature T, it has been described by Max Planck by this expression here that depends on the temperature as well as the wavelength. So what do we mean by spectral excitance? That would be the power that's emitted by the radiation source in one unit area and a unit wavelength. So that's the definition, and it is and this is what you see here. All right, then let's look at what we call as Wayne displacement law. Now this would be to map the peak of each of the blackbody radiation spectrum. As you can see here, this dotted line here mapping the peak, and you find that they actually drop as the temperature decreases. So how do we get this? In order to see this relation, what we do is we differentiate the spectral excitance equation from the previous slide and setting it to 0, then we will then be able to get this displacement law. And to simplify it, the relation will be given by lambda maximum, that is the wavelength at which maximum radiant excitant occurs, multiplied by the temperature of the blackbody radiator, and that's equal to a constant, Hc divided by 5K. So another expression that we will get from this is by summing up all the radiant excitance, that is to integrate over all the wavelengths, then it will give us the total excitance, and we will come to Stefan-Boltzmann law, whereby the total excitance is equal to a constant, which is Stefan's constant, multiplied by the temperature of that radiating body to the power of 4. Okay, now if this black body is not radiating perfectly, then we call it a gray body, and we can define a certain term which is called emissivity, which is given by the ratio of the radiant excitant of this object divided by the radiant excitant of a perfect black body that is at the same temperature as this particular object. So we're going to look at sources of electromagnetic radiation, the non-laser type. So firstly, we'll look at a very important natural source, that is the sun. So here we have the emission spectrum from the sun. This line here is measured outside the atmosphere, and here it is measured at sea level. So as you can see here, when it actually extends from about 200, 300 nanometer up to about 2000 or 2000 something nanometer. And the visible range is between here to here. Here is ultraviolet, here is infrared. And expanding the visible range here, at least narrowing it down, we have this curve here. And the color spectrum is also given here. So these dips will be seen as dark lines appearing in the colored spectrum here. As you can see here, the spectrum here is a continuous spectrum. And as far as sunlight is concerned, the Earth receives an average amount of irradiance of 1,350 watts per meter squared. This is an annual average value, which is called the solar constant. And now we go into artificial sources. In the old days, when I was kid, we never had fluorescent lamp. It was all incandescent lamp. As you can see, the spectral emission from this incandescent lamp covers the range of visible up to infrared. So usually when we have a 120 watt bulb, you can feel the room can get a little warm. And here we have LEDs. Now LEDs can emit light in a very narrow range of wavelength. For example, the gallium arsenide here, the emission is between about 940 if you take the full width, half maximum. Full width is about 904 to about 905, slightly more than 905. So it's only about 1.5 nanometer width at full width, half maximum. And here we have the fluorescent lamp, which you are very familiar with. If you look at the emission spectrum fluorescent lamp, it has a continuous spectrum here, which is mostly in the visible range. And besides that, it has some peaks, very narrow peaks. Now, these are emission lines due to de-excitation of electron from between two energy level in the mercury atom. And these are discharge lamp. Basically, it's an electrical discharge, as in plasma produced from, in this case, it's a xenon. It has xenon gas. So these peaks here are emission lines which is characteristic of xenon gas. Okay, next we look into detectors of radiation. We need to measure the radiation we receive, the incident radiant energy. So we need something that's reliable. Well, of course, we can use our eye, but it is very subjective, and we could not give the quantitative amount of brightness or energy level. We cannot say always bright, always dark, or it's so dim. So, and it's subjective. So we need a reliable detector which can give us quantitative numbers and is objective. So some of this, we can divide that into two groups, which is thermal detectors. It responds to change in temperature. But this type of detectors are slow in its response because it has to be measured in terms of change in temperature. Some of these examples are thermocouple, where we have different material here and two junction, for example. And then when we place these two junction at two different temperature, it would generate an electromotive force you measure as a voltage, potential difference between the two. Or we have an array of this thermocouple, and we call it thermopile. Or we have what we call bolometers and thermistors, whereby the change in temperature will bring about a change in resistance. And we measure the change in resistance instead. And in bolometers, the sensitive element are metals. In thermistors, the sensitive element used are semiconductor materials. For pyroelectric detectors, well, the temperature is dependent on charge separation. And in pneumatic or Gauge detectors, then this will measure the thermal expansion of gas that's induced by the radiation that's incident onto the gas cell. So you can see that this would definitely slow down the response because it has to convert to a different means of to exhibit it in a different entity. Now, then we have the quantum detectors, which are fast detectors, and they respond to the rate of photons actually falling on them. One of the examples are the photoemissive detectors, whereby electrons are emitted from the photocathode. They are light sensitive within certain wavelength range though, and then they will, light falling on it, overcome the work function and they release electrons. So these are in like for example diode phototubes, photon multiplier. Well, in photon multiplier there will be some diodes here which actually multiply the number of electrons so that at the other end it would be at a value that is detectable. Photoconductive detectors, for example, these are usually for wavelength in the infrared range. Photons are absorbed and it will produce additional free charges, so it has increased in conductivity. So material used are those that are listed here. And there's another detector which is a photodiode, which I think you're familiar with. Is you can either operate it in the photovoltaic mode or the reverse bias, which is called the photoconductive mode. This is when light falls on it, then you have conduction and you measure the voltage drop here, or when you reverse bias it, so when light falls on it, become conducting, then you actually measure the current. We were talking about light and light sources. Now, have you ever heard about light pollution? Now, on the screen here, we have the World Atlas of Artificial Night Sky Brightness. These are all due to artificial light. And this has been collected by what we call citizen science. So we have data being collected from people all over the world. And here is the map that shows where at night, where are the parts of this world where we have extremely lots of artificial light. And because of this artificial light background, we actually lost our ability to view the beautiful natural sky. Now, so what is light pollution? Okay, light pollution actually brings about a lot of problem. Yes, at night we want to work more time, we need more time to work, so we have artificial light. But this has brought on a number of problems because in order to light up the night, we have to use energy, right? And in the olden days with an incandescent bulb, for a room, a simple room like our lecture hall maybe, we will need probably about 2 incandescent bulbs, each of 120 watt. But now, of course, with the fluorescent lamp, if we have about, let's say, 6 pieces at about probably about 18 watt each. So let's round out 20 of 120 watts, about half the amount. But of course, with even improvement in further lighting, like using LED, then it can even be further reduced. So next, here is the collection of data for monitoring the global night sky. So, and this is the effect. If you have a background of bright light, then you look at this. This is what we should be able to see. But nowadays, in the city of Kuala Lumpur, you hardly see any of the stars. Likewise, here another picture of the beautiful Milky Way, and that disappears from sight with bright lights from our homes, our street lamps, and all that. So, in order to bring to awareness, besides light pollution, that also indirectly lead to other environmental problems, we have what we call the Earth Hour. I think most of you would know about this. So the Earth Hour for this year will be carried out on the 28th of March 2020. And from 8:30 p.m. to 9:30 p.m., you turn off the lights and you turn on the stars. Well, when you have the time, you can watch the promotion video here. And of course, you can also go to Earth Hour ORG here to have more information. Now, besides losing our night sky visibility, then we also have other problems that arise from light pollution. For example, the birds, the migrating birds, get confused by the brightly lit buildings, and some of them just crash into those buildings. And then to human health as well. We have a hormone called melatonin, and when the eye signals that it's dark, melatonin will be synthesized. And this production of melatonin, it peaks between 1 to 2 a.m. and it shuts off during the day. So it's like our time pace clock or something like that, that tells us it's darkness, it's day and night. So that's why it's sometimes referred to as the hormonal expression of darkness. Now, melatonin has benefits, a few benefits to us. It boosts our immune system, lowers the cholesterol, protects our cardiovascular system, stabilizes our biological rhythm, and even restore the night cycle of rest and regenerate of cells that are under stress. Now, in the absence of this, then a person can suffer from various problems. Now, one of that problem is it has been found, there are research that finds that melatonin actually inhibits the growth of different tumors. So without this hormone, chances are that you are giving room for tumors to grow. So please don't stay up late into the night every day. Once in a while, when you need to meet your assignment, that's fine. Of course, we have new lighting designs, eco-friendly type, energy efficient type, for example, like LED lighting, and architectural design that take into consideration or make use of the natural lighting as well, so it becomes efficient eco lighting system. Okay. All right, let's start on, we have done the introduction. So now start on geometrical optics, or what we call ray optics. Now this has to do with ray treatment of light, and in the first degree approximation, and we assume that light would travel in straight lines in a homogeneous medium. Okay, the first law that we're going to learn would be law of reflection. So when an incident ray were to hit a surface, it will be reflected, and the angle of reflection will be equal to the incidence angle. And you all know that. Now, another requirement of this law is that this ray, incident ray, and this ray, the reflected ray, as well as the normal to the surface, they all lie along the same plane, which is this plane here. So, and this plane is called the plane of incidence. So that's another requirement for this law. Next, we have what we call as specular reflection. Now, you get specular reflection where the light ray is reflected on smooth surface. So, and all the rays in this parallel beam, for example, here we expanded it, all the rays in this parallel beam, they obey the law of reflection, of course, and they result and they produce a reflected ray which is also parallel. So this is called specular reflection. Now, what happens when the surface is not smooth, it is rough? If you look under the microscope, then the surface would have unevenness. So if you consider a parallel beam with a beam of light with parallel rays actually, so when it hits on this surface, then it gets reflected here. Law of reflection, mind you, law of reflection is still applicable. But when it hits here, it gets reflected this way. When it hits at this surface, because of the inclination at the point where it hit the surface here, so you draw the normal, you have the incident angle and the reflected angle is the same, but this ray will be reflected in this direction. In this case, it gets reflected in this direction. And here it gets reflected in this direction. And this ray, it gets reflected and reflected again, and it comes out in this direction. So in other words, what we get is diffuse scattering. So you will not be able to see the reflected beam clearly. It gets reflected in many directions. So what you get is diffuse scattering of the original parallel beam. Now, if we assume specular reflection, so we can then describe the direction of the light ray by using unit vector. So in this case, we have a ray that comes in this direction with the coordinates x, y, and in a negative, going down. So it's negative z direction here. So that will result in a hitting at point P, and it will result in a reflected beam, which will be at having a coordinate x, y, and positive z direction. And if we consider a sequential reflection, so it reflects on this surface and this surface and this surface, and then it goes out. So usually we get this when we have a corner reflector. Now, if you look at this, the incident ray hits the YZ plane, and then it gets reflected, and now it hits the XZ plane, and then it gets reflected from here and it hits the XY plane, and then it exits. All right, so if you look at the coordinates here, starting from a direction in negative x, negative y, negative z or z, then the output ray, the reflected ray, will be in the positive y and z. So the ray returns precisely parallel to the line of its original approach, only it is in opposite direction. So this is very applicable for highway reflector. So it uses your high beam or your headlights to reflect that light back to you, so that you don't hit those divider or barrier at the side of the road. Now, let's talk about image formation in plane mirrors. Okay. So we are talking about reflection of point object. Law of reflection here will ensure that now when we have here the source, the point object, so light rays from this object point, if it falls directly perpendicular to the surface of reflection, then it gets reflected directly along its path. If it gets reflected at another point, then you get reflected here, and you will take a ray which is coming from a larger angle here, it gets reflected like this, and then by projecting this reflected ray backwards, and then you'll find that they all meet at a point here. Now, this point here will relate to the image. So what you see is as if the point object now is behind the mirror. It's as if it is behind the mirror. Okay, so in this case, this image now is virtual and you cannot project it onto a screen. It's like watching your image in the mirror every day in the morning. Now, another image formation in plane mirrors, another characteristic is that if you have an extended object, that means you have an object which is not a point but has got an extended length. Well, you can take the ray from the ends of it, okay, and then you trace the reflected ray. You'll find that the image is still formed behind the mirror at equal distance from the surface of the mirror. Another feature of the reflected image is there's a left-right inversion in the mirror. So when you stand in front of the mirror, what you see of the image of yourself is that your right hand seems to be the left hand of that image. What if your object is not directly above the mirror? So that's easy. You just have traced the ray that would reach the mirror, and then you get the reflected ray. So again, by projecting backwards, again you can trace where is the image position. Okay. Now next we talk about internal and external reflection. When we talk about external reflection, it means that our ray is incident from a medium which is less dense and then coming to hitting an interface, and the other side of the interface is a medium which is denser. For example, this is air and this is water. Refractive index is 1 here and refractive index here is 1.33. So you get a reflected ray. Now, law of reflection holds incident angle, reflected angle equals to incident angle. Sorry about that. And then, but the reflected ray itself will undergo a phase change of pi. However, if you have internal reflection, that is, the incident ray now is coming from the medium of which is denser, like water, and then it hits the interface between that separates this denser medium with another lighter medium, less dense medium, and it gets reflected. Of course, this angle must be larger than critical angle, so we'll talk about that later. And law of reflection still holds, but the reflected ray now will not have any phase change. So this characteristic here will be important and need to be considered when we are working on the topic on interference of light. Okay, let's look at the second law that in geometrical optics, presented for geometrical optics, which is the law of refraction, or otherwise known as Snell's law. Now, I think you are all familiar with that. You probably have in your mind already. N1 sine theta 1 equals to N2 sine theta 2. But what's N1? What's N2? What's sine 1? What's sine 2? What's theta 1 and what's theta 2? Sorry. So let's see. Now, it means that basically what it means that the ratio of the angle of incidence, so we have this ray that's coming in, so this is the angle of incidence. You draw a normal to this surface, and then of course you have part of the beam being reflected, and reflection law applies, and part of the beam can be transmitted into the second material. And you have a refracted angle or a transmitted angle. So there is a certain relationship between this angle and this angle to the refractive index of the medium on top of this surface and the medium below this surface. So we'll find that the ratio of the sine of the incident angle to that of the sine of the transmitted angle, that will be equal to the ratio of the refractive index of the medium, the second medium, to the refractive index of the first medium. And of course, there's another criteria to this law, that is the incident ray the refracted ray and the normal to the surface, they all lie along the same plane, which is the plane of incidence. This is similar to our reflection law as well. So next, let's consider refraction through plane surfaces. Now let's look at this diagram here. We have a plane surface here separating N1 and N2. And let's say this water, maybe this air, we have a fish underneath here. So a ray that comes from the fish, incident onto the surface, normal to the surface, will then pass through the surface without deviation. It will go straight through. But a ray that is at a certain angle, this angle here, will then meet the surface here, and then it will bend. If this is has a refractive index which is smaller, that is a less dense medium, then this transmitted ray will then make a larger angle with the normal. As you increase this angle further, then this angle θ2, angle of refraction or transmission, will also increase further. Projecting all this transmitted ray backwards, you find that they don't meet at the same point. So there's no unique image point. Okay, so what do we do? How do we consider? How do we treat this problem? Now, before I go into more explanation, here is a question posed, which is question 4 actually, on jungle survival skill. You can read it on your own and you can then answer the question. Now, if we were to go, if we were to consider para-axial rays, that are rays which are very close to the central axis, which the normal here, which is the central axis, where there's no bending here in this case, which means that this ray here, of course, this diagram is drawn with over-exaggerated so that we can see this angle clearly, but in actual fact, if they are very close to this central axis, then this ray should be drawn very, very close, making a very small angle or very, very small incident angle. So that sort of narrowed down our, we are making an approximation, okay, here. So in this case, if you look at this diagram, okay, so let's say this ray is incident onto this interface at this point P here. No P, it's not written any P here, at this point here, and then it gets transmitted. So this is the transmitted angle, this is the incident angle. Projecting this transmitted beam backwards, this θ2 is the same as this θ2, but we have, it meets this normal or the central axis at this point S prime, okay? Now, if this angle is small enough, then sine of, we can do the approximation here. The first approximation, we can take sine of the angle to be almost equal to the tangent of the angle, or almost equal to the angle if we put the angle in radian, use the unit for this angle in radians. So from Snell's law, then we can approximate it to n1 θ1, drop the sign, equals to n2 θ2. And we replace this angle with the appropriate tangent. That will give us, now if you consider this distance x, so we will have n1 x over s is equals to n2, tangent of this one will be x over s prime, tangent of this x over s prime. So we have, then we can locate where would that image be, which is at what depth from the surface of the interface is located the image. So we have S prime then will be equal to N2 over N1 multiplied by the actual depth of the object. So in other words, this is what we call the apparent depth. That's why when you view an object which is in the pail, for example, at the bottom of the pail, or you drop a coin into the bottom of the pail, you'll find that this coin appears to be nearer the surface than it actually is. Basically because we have this. N2 is 1, which is air, N1, which is the water, and this ratio here is less than 1. So definitely S prime will be smaller than S. If N1 is smaller than N2 and your incident beam coming from medium N of N1 here, then your bending of that refracted or transmitted ray will be closer to the normal. If the incident beam is coming from a medium of denser, coming from a denser medium, then the ray will bend further away. The resulting transmitted ray will bend further away from the normal. Now let's come to critical angle of incidence. So if you look at this diagram here, as we increase the incident angle, it bends away. It bends more from the normal. This is from denser medium to less dense medium. N1 is larger than N2. And then up to a certain point, you find that this ray now will then, the transmitted ray will then be along the surface that separates the two medium, making a transmitted angle that is 90 degrees. So at this point, this is critical angle. Just tipping it a little more than critical angle, then you find that this beam will not escape. It will be reflected into the water. So we have total internal reflection. Now let's consider this one. At critical angle of incidence, then we have sine N1 sine theta c equals to N2 sine 90. Sine 90 is 1. So we have sine theta c equals to N2 over N1. And then you have theta will be the arc sine of N2 over N1. Okay. Now this total internal reflection will occur only when N2 is larger than N1. And remember, we said this is internal reflection. So this reflected ray here will not have phase change. Now, along with that concept that we just learned, this is one of the manifestation of that concept. You are underwater, swimming underwater. You look up the surface and you will see a circle. This is called Snell's window. Well, you can perhaps explain on your own, think about it and explain and find what exactly, why is it limited view here? Okay, what can you see also? Think about it. Now, another thing we're going to learn here is principle of reversibility. So if you look at this here, now something is not right with this diagram, I would say. This diagram is wrong. We should not have ACB. We should not have the ray AEB. We should only have the ray ADB because the others will not obey law of reflection. So those two rays are wrong. Only this one, ADB, is correct. So look at this. The incident angle equals to refracted angle. So light travel from A, touches point, reflected at point D and reaches B. And if turn around, if B is the source, light ray, follow the same path, reflected at D and reaches A. So that's reversibility.
This is a corrected diagram for the reflected ray.
And if you look at transmission refraction, then we have A, source of light. The ray come from here, enters at this point O, and enters into the second medium and reaches point B where you get the image. On the other hand, if now this image point becomes a source, you will follow the same path and reaches point A. So that is the principle of reversibility. The ray will retrace its path. So these are listed the entire learning outcomes of this lecture. Thank you for listening.